Welcome to Lecture 13. Today we'll be covering the launch vehicle design part 2. And we talked about what a launch vehicle is about. You have the first stage engine, the side rocket motors, the first stage fuel tank, the intertank, the first stage oxidizer tank, the interstage adapter, and then you have the bottles that could contain the hydrazine. You then have the fuel tank, again for the second stage, the payload attached feeding the spacecraft and payload fairing. And so what we're trying to do with these structures, we're trying to design them so that when they experience the launch vehicle ascent environments or even ground environments, that these vehicles can survive and it can deliver the spacecraft to the correct orbit. And we talked about how vehicle vibrations uh, can be a problem. And so we use something called the coupled loads analysis, which is a dynamic analysis that entails taking a simplified finite element model of the launch vehicle, a simplified finite element model of the spacecraft. We attach both of these things together, and then we analyze the whole trajectory to space to ensure that none of these parts will break. But to do that, I have to really extract the bending moment, the shears, and the axial loads across the vehicle. We learned in the previous lecture how to do that by hand. You guys saw that. We learned about that. That's a free body diagram done by hand at max Q. You can do it at different points in the trajectory, but that model is only good for preliminary design. It's not good for highly accurate loads for design. And so that's where coupled loads analysis is called coupled loads because the launch vehicle is attached to the spacecraft. So it's coupled loads in that sense. It's coupling the launch vehicle response to the spacecraft response. So that's one aspect of what we talked about. And so our goal is to figure out how to qualify a system that has these loads and what to do with them. So it's a three-prong approach that we use in the design of launch vehicle applications and also aircraft as well. The three-prong approach is the structure qualification testing, the structural analysis, and then the structural acceptance testing. I'll walk you through each of these very carefully. The adequacy of the structure is defined via design qualification and hardware acceptance. You want to make sure that the design is qualified to survive the part-to-part variability, because every time you assemble parts, you're going to have build-to-build tolerances, but you're going to have part-to-part variability. And so you also have uncertainty in load paths. And so the qualification testing is helping you with that. It's trying to help you with ensuring that the design is robust to all these variabilities. The flight hardware, I will talk about that later, is accepted through screen out the poor workmanship that could occur. Verification of the structure is basically done through considering all the potential failure modes and all the potential load conditions. Potential failure modes include detrimental deformation, material yield, ultimate failure, structural collapse, buckling, fatigue, and delamination. So you want to make sure that that qualification testing is exercising the most critical failure modes. Now, a qualification test may not be able to qualify all the different failure modes, but those that cannot be qualified in the test should be done and qualified by analysis. The load conditions that you may include in this qualification test is going to be usually a static test. Usually we don't do a dynamic test of a launch vehicle part. Instead, we apply the loads statically. And what that means is I'm taking the static loads and the dynamic loads, the bending, the shear, the axial loads, the acoustic environments, the pressure, the temperature, and I need to come up with a set of static loads I can apply to my aircraft or launch vehicle. And again, I cannot apply all these loads that are in flight, but I can find ways of applying them equivalently. Say, for example, the temperature of a component is at 300 degrees F, and it's a huge component, and I cannot do that test on the ground at 300 degrees F. So what I need to figure out then is how can I apply the loads so that the structural margin of safety, so that the margins in the test are enveloping the margins in flight. And that could mean increasing the loads to account for the temperature difference. How the temperature difference can play a role? Well, if the temperature is higher, perhaps the strength is lower. And so what you can do is come up with a test that when you do it at room temperature, it accounts for the difference between room temperature and 300 degrees F. So that's one way to do that. Perhaps it's gravity, gravitational load, or some other load, G loading. Well, I cannot apply G loading to our aircraft or launch vehicle on the ground, but perhaps I can adjust the loading I apply to my structure to account for the fact that you have the G loads applied to the component of interest. And so the loads are defined through the couple loads analyses. We talked about that. The structure qualification tests are quite important because the structure qualification test, which can be done through a single article or multiple articles, demonstrate adequacy of the design for a nominal build. It provides a verification of your workmanship process, that the way you're making things makes sense. That's why you saw through a few examples I gave that there's aircraft failures during ground testing, and it makes a lot of sense because if you do want to qualify a system, you also want to make sure that you qualify the manufacturing processes. You also want to provide qualification margins above limit loads, and you want to make sure that you can have a way of anchoring analysis to testing. So the testing can be instrumented sufficiently with strain gauges, deflection gauges, and digital image correlation, which data can then be used to correlate the analysis. Very important consideration here. The structure qualification testing is usually a full-scale test of a launch vehicle structure or aircraft like a wing, and the approach is used to qualify the ultimate strength of the design. The test factor typically used for unmanned vehicle or vehicles that do not have humans in them, the test factor is usually 1.25 for launch vehicle design. And it needs to account for the differences between flight and test, and that could include boundary condition differences and environmental condition differences. The AIAA S110 standard is a governing standard for launch vehicle design. I'll be going through a standard today, a NASA standard, and I'll walk you through that standard so you can see what their factors are. Combined loading may require facilitating and reproducing flight-like stresses in critical areas. You may need to figure out a way of combining loads in a smart way. And that's not always very simple to do. A good practice, but it's not standard, is to load the test article failure beyond the required ultimate load. It will help you identify and demonstrate the most critical failure modes. That's one thing. But if you don't test it to failure, then you don't know what the critical failure mode was. Maybe it was buckling or fiber failure or delamination. But if you don't take it to failure, you will not know. And so there will always be that thing of, I don't know if my testing got to the correct critical failure mode I predicted. Because remember, analysis also plays a role in trying to come up with the critical failure modes you want to test. So it's a chicken and egg problem where what comes first? Typically, you do the analysis first during the PDR and CDR, and then you step into test. And you want to make sure that in the analysis process, like in the critical design review, when you present your analysis, that analysis can list all the critical failure modes, that you've identified the most critical ones you want to test, and then your test can actually achieve those critical failure modes, can exercise those critical failure modes. And you don't know if you achieve the critical failure mode or not if you don't test it to failure. And so there is an advantage to testing to failure. A disadvantage of testing to failure is that the test article has been destroyed. And so therefore, if you want to go back and look at it and perhaps do other things, the article is gone and you may not be able to do it anymore. So that, just take a wing, for example. The critical failure mode of a wing could be the base of that wing. And so you want to then test this tensile or compression loading of that particular wing. It's good practice to keep the failure away from areas of complexities, because if failure happens in areas of complexity in your design, then it's going to cause you to have significant issues with correlating your analysis, but also you're going to have more uncertainty in those areas. If you look at AIAAS 110, it recommends to keep failures in areas that are simple to analyze. And that's actually very advantageous. It helps you because it promotes simple and repeatable failure modes. Um, if the failure occurs in a particular complex region, you don't know what the sequence of failure events could have been. It could be a combination of fiber failure, matrix damage, or something like that that makes this assessment quite complex. The structure qualification testing establishes the ultimate capability so that the residual capability can be used to assess production issues. It facilitates cutting of coupons from test articles to ensure as-built hardware is consistent with the drawing. So again, once the test article is failed, one approach is to go ahead and cut the coupons from the test article and just make sure that all the thicknesses, the plies is exactly how you wanted it, that everything is exactly how you wanted it. And a good practice, but it's not standard, is to use a test article representative of an already available production unit that have undergone similar flight-like processing. The issue is that you may put a lot of effort into making your first article, but less effort into the subsequent articles. That can be a problem because you may go into the design thinking, well, I tested it. I tested, one of the articles and it passed the test. But what happens with that after the first article, your vigilance goes down, your vigilance, and you may not do a good job anymore. And so that's where uh, testing a representative article of your production lot makes total sense rather than testing the best one. Again, the goal is not to test the best one, but yes, I want to test to pass. I want to be able to pass certification, but you could also fool yourself, and then you don't want to go into a flight failure later because you tested the best one, and perhaps you could have had one that's not as good. Um, Structure analysis also needs to be performed, and the structure analysis can be looked at. It has three key ingredients. We have the predicted limit stress, so that's the high stress that the structure is going to see based on a statistical allowable, not statistical allowable, but a statistical analysis of the loads, a factor of safety, and a material strength. So let me talk about the marginal safety calculation. Marginal safety calculation is strength divided by limit stress times the factor of safety minus one. You typically want to have a margin of safety greater than zero, and ideally 10 to 15% in case something happens, like a non-conformance or a tool drop or something that was not good. That's where that can be very beneficial, is to have that extra pocket margin in case something happened. Let's examine this formula very carefully. If the stress is too high, times the factor of safety, and this multiplication is greater than the strength, you have a negative margin of safety. And so, as a consequence, you may want to either reduce the stress or redesign the structure to reduce the stress, or come up with a different material system that gives you better strength. So, when I look at the strength numerator here, the strength you're going to have to start looking at different failure modes. And so, interlaminar failure, core failure modes, all those, for example, as an example, are going to have a particular strength. And so you want to quantify what that strength is, and then you will determine the A basis strength, which is true for a single redundant load path problem. 95% confidence with 99% that the samples will not exceed that particular allowable. And you do have to characterization testing. A B basis allowable, this is more of a summary because we covered that. A B basis allowable is one where uh, you will apply to, and it's less conservative, it will be applied to areas where you have redundancies. So that's material strength. The main key point here is to get the A basis for every single failure mode you may have for the structure, and that'll populate the numerator here. Then you have the factor of safety right in the middle, but let me cover limit stress first. Limit stress is going to give you is the stress coming from the limit loads, which is defined based on statistics. And you want to just again make sure that, as an example, that the loads do not exceed with 99.7% of the time with 90% confidence. Typically, these loads are derived by the loads group, and you usually account for the maximum expected pressure in worst case thermal environment. And that'll give you the limit stress here that needs to be plugged in here. The factor of safety, on the other hand, can range, and I'll go through some of that today. You have the manufacturing variability, geometric variations, material properties. So the factor of safety is accounting for some of that. But you also want to make sure your factor of safety is sufficient to account for all of this, because you can imagine a launch vehicle designed only to a factor of safety of 1.25. That doesn't give you a lot of room for error. So you better make sure your manufacturing processes are well controlled, that your geometric variations are relatively controlled, and the material properties are not varying all over the place, because maybe your factor of safety will not be enough to account for this manufacturing variability, which can also include build to build variability. You also have the factor of safety, which should account for some amount of analysis and design uncertainty. Anytime you take you idealize a structure, you're going to make an assumption, and so that's where the factor safety can help a little bit. Is that it will forgive you a little bit for some mistakes, but not mistake, but assumptions, because mistakes should not you shouldn't have mistakes. We don't want that. Then you have the analysis limitations, the fact that you have a strength in the article, but you had a coupon strength that was determined through material testing. And so again, that's an analysis limitation, because you can't really analyze what's actually in the hardware built already, but you can only analyze uh, data based on coupon testing. One approach that people could use is, say I have a cutout for a window of an aircraft. I take that cutout and I'll test that cutout to really understand this, how that strength compares to the allowable strength that I designed for. You also have the issue of unknown unknowns. You may think you know everything, but most failures occur because we didn't know everything. And so the factor safety also helps you with accounting for uncertainty in critical failure modes. In the aerospace industry, you may have two camps. One camp may say, don't apply the factor of safety to thermal loads, because the thermal loads are self-limiting and they're displacement driven. The counter argument to that is that, excuse me, the counter argument to that is that there's variability um, in the material properties and geometric variations, and just because you didn't have it's a thermal displacement driven problem, it doesn't mean that the stresses induced will not have variability, and they will have because of the assumptions made. So all these three come into play into your margin of safety calculation. So let's look a little bit at the role of analysis. What is the purpose of even doing an analysis? The purpose of analysis is to determine the structural capability under nominal and dispersed operation conditions. Here you can see we disperse the loads, we disperse the strength, and now this margin of safety is accounting for these dispersions indirectly in this calculation. Because here you have a 9990 loads, and on this strength you have 95% 99. So 99.95. The analytical margin calculation are instrumental in designing evaluations. The analytical margin calculation allows you to determine the critical margin conditions for the various failure modes, and that's going to help you define the test program successfully. It helps you uh, judge whether critical failure mode is fully tested. For example, if I have 200 load cases And a lot of those load cases are targeting different failures like buckling, bearing, net section failure, fiber failure, matrix cracking, delamination, buckling, creep. Well, the analysis can help you to determine whether that test correctly achieved the critical failure mode. Recall that flight and testing is not going to be the same configuration. One of them is flying, and the other one you have to test on the ground. And so that's where the analysis can also help you, is to build that confidence that your test is enveloping the flight conditions. You also rely on analysis to account for hardware variability that may not be captured by analysis, by the testing. As you can see here, this test qualification here is of a single unit typically, and this qualification here is done on a single unit here typically, which may not contain the variations from flight to flight article. So therefore, the analysis can help you look at the hardware variability through an assessment like that, because here I'm gonna have a factor of safety, here I have the material strength accounted for, and the dispersions in the loads. It also allows you evaluating geometric and material properties. Say that the thickness came out lower than what's in the drawing. So that's where analysis can help you with. Analysis also helps you evaluate nonconformances at various processing stages. So examples of that could be, say, that there's a hole that was oversized. Well, the analysis can help you evaluate that condition due to that error, that discrepancy that we have. During the pretest phase, you assume that the model includes the proper physics and load paths, but you may be incorrect. So some organizations will use a factor of safety, an additional factor for uncertainty, or modeling uncertainty factor. During the post-test phase comparisons between analysis and test, here, during the post-test, you want to compare now your analysis to test and adjust as necessary, because at the end of the life of the program, at the beginning of the life of the program, you want to have a robust analysis tool that can be used to assess non-conformances and issues that may come up. And so I cannot emphasize more the role of analysis in forming this qualification testing, in helping you come up with the load cases that need to be tested. You cannot test every single load case, but you can come up with a smart set of loading conditions that together show and can be shown to envelope flight conditions. I also want to point out that the analysis and qualification testing may not match, and it may not match for many different reasons. For example, strain gauges could be installed in areas of high gradients. Well, a strain gauge orient in an area of high gradients of strains could be a problem, because the analysis may not be accurately compared to the strain gauge that's in an area of high strain gradients. Another one could be the strain gauge positioning is off. That can also reduce the ability of matching analysis to test. Third, the channels on the strain gauges could be off as well. And I can keep going off and on and on and on. But there's many ways where the analysis could not match the testing. That has nothing to do with the analysis itself, but maybe it was the way the instrumentation was installed. Analysis also is used to define the acceptance test conditions, which is your proof test before you fly. And so that's an important test. And so the analysis can help you shape that. The analysis of the acceptance testing is usually very simplified. It's a single test, load case, something very simple to look for any issues that could be more of a bigger scale problem. Let me walk you through example number one of the process of calculating the marginal safety. So you have your CAD model from the pressure vessel, say. You input the relevant geometry, radius, thickness in this case, and then you have the limit load condition. In this case is the maximum pressure this vessel is going to see. So this maximum pressure, you know it, you know this geometric data, you can now estimate the hoop stress, or we can use a finite element model, but let's it's a hand calculation. The stress is pressure times R over T. Perfect. Separately, I want to go through the different failure modes I could have and making sure I have the right material and strength data for all the materials I'm going to be using, for all the potential failure modes I may have. You want to collect this data and make sure you have it. This information is going to help you come up with the critical failure modes for the structure. In this case, if it's a metal, I'm going to say that is no yielding is allowed and that I don't want an ultimate failure. Simple, two failure modes. But I could have more. I could have buckling. I could have different ones. And so then I take that information and make sure I do calculations for each of the failure modes. In this case, yielding an ultimate failure can be quickly evaluated just by looking at the hoop stress. So then I'll take that to the next step and then come up with the A basis or B basis to calculate the margin of safety for each of the failure modes. In this case, the two failure modes are yielding and ultimate failure. I can take now that information and determine the adequacy of the design based on that data. But I first need the factors of safety. So again, three things coming in here, very similar to what I have here. Three things come in here: strength, material strength, factor of safety, and then the limit stress. And then the same thing you can see here: strength, limit stress, and factor of safety, all coming together to try to size the design to have a positive structural margin for the design that's adequate. In example number two, slightly a little more complex, but it's worth covering. You have the CAD model, you have the composite layup, you have the limit loads, which is temperatures and external loads. And now these three things come together, and then you develop a finite element model. And this is something I actually worked on before. This finite element model now has to include elastic properties for the foam, composite, and metal. Well, here now I have multiple different failure modes. I have the foam failure, the composite failure, the delamination, the matrix cracking of the composite, the bearing failure of this coupon here, this bolt, bolted connection failures, and so on. So I want to make sure, and I'm simplifying it here and just focusing on the stresses of the foam because at the time, the critical failure mode was found to be the foam failing. So you can do the testing to validate that failure mode, and if the testing did validate that, you see a crack where it's gray here, which exceeds the allowable of the material. And now again, the same approach. You validated the model. The stress now is an input. The strength is an input. The factor safety is an input. Now I can take that information, calculate the margin of safety. New structural acceptance testing is quite important, and that's basically making sure that your structure that you manufacture. Now you look at the manufacturer flight article now, not the one you qualification tested, but now the flight article that that you produced. That's the one that's going to fly. So you want to make sure that you have in-process testing, meaning I'm going to make sure that the processing of that part is correct, and you can verify that through tagging testing, cutting panels out. For example, if I can cut parts that are not going to be part of the flight design, I can test those to make sure they're okay. So some people design a little bit over designed in size, so you can cut off and machine areas where you can then take those coupons and test them further to make sure that the part came out as intended. And Dr. Rome talked about that a couple of weeks ago. Witness panel testing is great. For example, if I cut a window out where the window goes in, that composite, say for example, that composite monolithic laminate can now be tested to make sure is good. And if it's not good, then you know something's going on with the production of your manufacturing floor. Proof testing verifies workmanship, and what that entails is applying a load greater than flight, and you do that to exercise not the critical failure modes, but you want to target the critical failure modes. This test is really intended to make sure that everything holds together, that your manufacturing process is robust. It's required for composite structures and bonded structures, not typical for metals. Non-destructive evaluation is recommended after proof testing because after proof testing, you could have some damage introduced by the proof test itself. And so that's where particularly composites. Um, all flight tanks and solid rocket motor cases tend to be proof tested, even if they're metals, and I'll be covering some of those requirements later. Non-destructive evaluation is basically looking for defects like wrinkles, delaminations, fiber failure. So the inspection method becomes important. The acceptance criteria also becomes very important, and it is required for composite structures. And it also recommended before and after proof testing. Say you have a weld and it goes through proof testing, there's a benefit in checking that everything held together after proof testing. So the quality of the flight hardware has to be inferred from in-process testing and inspection because you cannot really take a flight article and test it to failure. That makes no sense. As a consequence, you have to put the effort of making sure that every flight article goes through some amount of testing that gives you the confidence that you have a robust manufacturing that came through for you. Structural acceptance testing is important. Qualification testing and design analysis only verify the design process, but the fact of the matter is that every hardware is usually imperfect. Manufacturing defects are bound to occur in composites and welds. Damage during handling and shipping and processes are going to happen. Hardware is not going to meet the design specifications often, and so that's going to produce non-conformances, also known as discrepancy reports. You can accept the hardware doing analyses of these issues that you find or by test, and you can validate the analysis. That's where validation of the analysis becomes so important because if somebody makes a part thinner and it was not thinner, then that's where you may have to make sure they use analysis to evaluate it. And so that's that. And uh, I hope that makes sense there for that portion. Um, you may have to reduce acceptable load limits during flight if you know there's an issue with the hardware and you cannot redesign. That would be a problem. Another approach is to reject the hardware altogether and just send it back to the vendor, or if it's in your company that made this large structural component, you may just leave it in the storage unit for doing some testing here and there, beating up a unit to keep learning. Repair restores the strength of the original strength, design strength. So if there's an impact damage event and the hardware is not meeting the requirements you need for that part, because you know you maybe have negative structural margins, you can bring a repair in to bring the structural margins for that flight article back up to par and making sure it's greater than the design specification. Pedigree reviews are very important. They verify the as-built hardware to make sure they function as designed. You're verifying material properties. You're verifying acceptances reports. You're verifying manufacturing process and deviations. And you're also looking at discrepancy reports and supporting analysis.